Okay, so let's talk about present day email as far as a problem with email itself today. It's more like a postcard than a letter. It can be read by any number of people in a transit. If recipient's account is compromised, it may be read by unauthorized persons. Network sniffing may capture and reveal content to unauthorized persons, like the man-in-the-middle attack. If we were to open up our emails on our desktops and converse back and forth to each other, we could be able to capture some of that data going back and forth, unless that data on that email was encrypted. Current protocols date back to 1970 on email, so way back when Netscape started, even before that, is when the email protocols started with SMTP, which is basically just open, unsecure, but it worked, and so that's why they started using it. And headers, especially like from, are ridiculously easy to forge. And what this is talking about is basically faking an email coming from somebody. Doesn't take much programming skills to change a from address to whoever. You can change it from Barack Obama at whitehouse.gov. And the person on the receiving side would say, oh, okay, it's from Barack Obama, and open it up. And think they got an email from the president. And it's really not. Yeah.
So somebody could easily get the name of another employee.
Yeah. Change it from address.
It's done.
Yeah, easy done. And it doesn't take much technical skills. It takes about a minute on Google to figure out how to do it. And so, pretty easy to do. And if the sender is compromised, it may not actually have sent it to that person. Also, how can you verify the sender's identity, that they are who they say they are? They're not a forged from. And so a whole bunch of things can pop up and do pop up in an email world. 90-some% of our email that we come into businesses are spam, like 96, 97, 98%. Is that right, Lou, for us still? And so I know at Aqua it's about the same. I talked to Mike at Entree a while back. His is about the same, about 97, 98% is spam mail coming in. And so, a lot of junk coming in, but there's also the need for security in email that we'll talk about. Also, sensitive and confidential data on hard drives. People carry around laptops, tablets. If the system compromised or stolen, lots of potential fallout. Even on the iPad and on the Windows tablets, both the emails are stored resident on the device. For pop mail, even IMAP will store some data, maybe the first 50 emails or something, 100 emails or whatever, to easily access it offline. So if the system's compromised or stolen, lots of potential fallout, permanent loss of irreplaceable or proprietary data, exposure of secret or sensitive information. Hopefully people aren't sending emails or data, storing data, you would think, on a company laptop, but that happens every day. They're storing confidential data. Maybe they shouldn't, but they are. Financial loss, disclosure requirements. If you have a business you're in competition with and they get this information, it could mean loss of sale, loss of customers, loss of your stature in that community for that type of business. And so the list goes on and on. It can happen. Also, data from the deleted files can be forensically recovered. We will be doing that actually in a few weeks here. I think next week or week after, be doing a lab where you basically do an index of the entire hard drive, and it'll kick back every word ever written to that hard drive, even though the person's deleted it and went into the system and deleted from the trash. It's still in there, and so data that's on the hard drive can be recovered. They also have what's called slack space allocated but not used. On Windows system, you can still have data from a deleted file, which we'll talk more about that when we do that lab. But data can even be recovered from a drive that has been reformatted, believe it or not. If you do a single format on a hard drive, there's still data resident from the last time that hard drive was used, if you use the right tools. There's tools we'll talk about when we do the indexing that are out there, where basically writes zeros over the hard drive multiple times. Like say it's 16 pass or 32 pass, zeros over every bit on the hard drive, which takes some time to do. But most users don't do that. They just reformat the drive and start over again, do a one reformat pass. How do you securely delete sensitive files? There's DoD standards, Department of Defense standards, which this PDF, by the way, will be on our, it's been Penn State, but it'll be on our lab file that you can click on. And DoD standards goes into how to delete sensitive files from a hard drive and securely do it. Solutions. Windows has a solution, EFS, which is a one-click encryption of individual files. They also have current, the bit solution that we use now currently on Windows 7 and 8. Still, a problem with that is there's encryption can be removed from the files copied or moved from a floppy, CD, USB, other media. Also, management of encryption decryption keys is not user-friendly on a Windows machine, even on the most current Windows. We talked about that when we did the, we talked about encryption here last week on the open source encryption. EFS can be circumvented if the administrator account is compromised, even on the current system we have with Windows 7, Windows 8. If the administrator account is compromised and thwarted, that administrator can go in and then manage all bit accounts on that machine. On the machine, the one we used last week, you could basically take, and the benefit of that one was, since it was a non-Microsoft encryption device and algorithm, those keys could be stored off-site, same you can do with Microsoft, but it's not tied in any way to the operating system. It's totally separate from the operating system. And so anything, and we talked about this last week, anything that's Microsoft related, good, bad, or ugly, people like it or don't like it, it can be compromised because hackers can get in and figure it out eventually, how to get in the back doors of those of Microsoft systems. Problem is not just Windows XP 2000 only, it's also with current systems. It doesn't deal with email at all, encryption on Windows, the default Windows encryption, no secured wipe capability as well. So there's a guy by the name of Phil Zimmerman in 1991, not been that long ago, that created what's called Pretty Good Privacy as a non-Microsoft and a just open source based on a public-private key cryptography principle developed by Whitfield Diffie. And it provides highly secure portable encryption and a signature for any digital included email. It includes a secure wipe utility conforming to the Department of Defense standards. It gives at least 3 passes or more. You can set it to go beyond 3 passes. And then available for all versions of Windows and Mac, even available for Linux. And it's a Linux product, so it would be available for Linux. And it's under the GNU Privacy Guard, which is open source consortium. Linus Torvald, if you've not heard of him, who created Linux, a young guy still. If you ever get a chance to read anything about him or about what he's done, there's actually a course on edx.org I'm taking right now. It's a free course. You guys can take it. If you want to find out more about Linux and how it started, it's edx.org. And it's a free, edX is basically a free online place for folks to take classes. And the classes you can take are from like MIT, Stanford, Harvard. And these are all professors that basically do video. You have reading to do, and then you have little chats to do and discussion. But anyway, what's cool about it is a lot of the courses on edX.org are totally free to take, and they're usually anywhere from 5 weeks to 10 weeks. At the end of the course, you get a little certificate they mail to you, or they email to you, and you can print it out, put it on your wall. You took your course in edX. And so one of the courses on there is actually on Linux. You can search for it. And Linus Torvald is actually one of the intro speakers for that course. I would recommend taking. I'm like about halfway through it. It's pretty interesting. He goes over why he created it. Where I'm at right now is he went over why he created it, which is basically a private project he was doing at the time, and then where it's at today and how it got there. And then he has, people within the Linux organization that goes and does the rest of it. But if you want to find out more about Linux, definitely edX, edx.org definitely is a great resource. Heard of that before, by the way? edX? It's awesome. Whew. I've taken like 4 courses through there. It's really good. Now, you can take paid courses on there, but I've taken all free courses on there. PGP drawbacks are it's not all user-friendly. You'll find that out Thursday. Public-private key concepts take some getting used to. Now, the one thing we won't do Thursday is technically, when you create your public-private keys, you're supposed to upload your public keys to a server. Like they have multiple servers you can upload them to, your public keys. But it takes a little bit to do that, sometimes maybe 5-10 minutes to do that. We're not going to do that Thursday for time's sake. I'm going to have you guys email each other your public keys. And then when the person gets the email initially that you're wanting to set up that private connection with, they have to download that public key that you sent to this cloud area. And then again, that might take 5 or 10 minutes. So the whole concept of just uploading, download public keys might take 10, 15, 20 minutes sometimes. So we're not going to do that Thursday. So that's where the not user-friendly part is probably. And also some of the steps change over time, and maybe the documentation's not that great. But hey, it's open source and it's free, and it works once you set it up. It does not scale well to large user groups because of the not being user-friendly part. Now, if you have a guru person that's really well-versed in, like the lab we do Thursday, it's probably an evolution of about 3 semesters work of putting it together and tweaking it, making it better. I have to change it ever so often, though, to make the steps to where it's easily set up. But Linux, if you ever took this course, you'll find out it changes probably more often than any OS does as far as updates, and the same goes with the software we'll be using on Thursday. It updates quite often. So because of that, steps change over time, and so you have to change them quite often. So, but once you get it set up in if you were to set up in a large organization or a large group, just as long as the IT folks are well versed and educated, which they should be. I've used it in organizations that have 100, 150 people, and it's been fine. But you do have to keep up on it. Now, it also requires understanding of and adherence to key maintenance and standards and practices. Like if your private key is lost, corrupted, or compromised, you have to generate a brand new one and start over on that trust relationship. So if Lou and I were to set up and I lost my private key, I would have to recreate a private key, send him again a public key, and reset up that trust again between us before we could communicate. So licensing, it's freeware on all versions of OS. It's supposed to be for personal use only. GNU, the GUI and the command line interfaces for US download and US only due to export reasons. Also, many countries importing and using encrypted software is illegal, like China. You could be put in jail for it. They want to be control over everything as far as your internet and all that. There's other countries, but that's one of the big examples. Commercial Windows and Mac versions are available. pgp.com. For a corporate license or commercial license is $50 per user. Now, I will say, if you purchase a license through the website, the steps are updated all the time on the website, and that's helpful for organizations wanting to use it. But for individuals like ourselves, we want to use it to communicate. Like if you have a business that you have that's LLC maybe, that you do contract work for people, say you're a graphic designer or you're a web designer, you could use this tool freely for your business, basically, for yourself. Beyond that, you'd have to buy a $50 license. GNU for Unix and Linux is free on the GNUPG.org. It's also available on the Mac on that website there, the SourceForge website. And there's also plugins. The one we're going to use is the email Thunderbird, which is free open source. Anybody used Thunderbird before or heard of Thunderbird before? It's a free email client, basically, that has calendar, email, and everything built in. And it is a portable version we're using. And the one we're using Thursday actually already has all the PGP and everything built into it. And so it's kind of nice. It's all out of the box, already ready to go. So let's start with some basics of how PGP works. The cryptography and high-level mathematics underneath it. We're not going to look at any high-end stuff. We're not going to have a pop quiz at the end of it. And so we're just going to look at an overview of it. So here's some words, quick definitions. Cryptography, the art and science of encrypting and decrypting secure messages. Cryptanalysis, the art and science of breaking cryptography. Cryptology, the mathematics of cryptography and cryptanalysis. Algorithm, a mathematical function process used for encryption, decryption, and verification. And key, a string or number used for character by character encryption and decryption. Before I forget, there is a machine way back in 1944 called the Enigma that was used by Nazi Germany to send messages back and forth to the troops. There was a gentleman that created a machine to basically about the size of this room to break the code. And there's a movie coming out. I don't know if you guys saw the stuff online about it, but if you get a chance to see, I think it's called Imitator or something like that. That's the name of the movie. Can't remember off the top of my head, but if you get a chance to see it, CBS.com I think had a news piece about it here recently, and so I definitely recommend. I saw the news piece Monday, I think it was, and so but is it Imitator, by the way? Did anybody get to see the article I'm mentioning? Let me pull it up here. I had it right here on my Mac. Excuse me. Imitation. The imitation game. Yes, interesting story. The gentleman died a sad death, but Imitation Game is the name of the movie. Imitation Game. And I believe it's coming out here. Let me see here. Alan Turing was the guy who cracked the code. And let me pull up the article here. He was 27, I think, when he was asked to do this, and he was an Englishman. The U.S. and France had basically given up that it was impossible to do. Let's see. Imitation Game out next month, it says, so it'll be out in November. And Benedict Cumberbatch is the gentleman who plays the Turing role, the Turing, Alan Turing, Turing, and he died a sad death, but did a lot. He like basically minimize a war 2 years or something, kind of caused it would have been 2 years longer. But because he cracked the Enigma machine and intercepted all the messages, because it changed the code every 24 hours. The encryption code was changed every 24 hours on this Enigma machine that Nazi Germany used. And so he created a machine that basically cracked it. And they had that in the hands to basically decipher the code, like, say, sending a missile to a submarine or something like that. And it shortened the war by 2 years because of his work. Out in the movie, and if you watch the video of why nobody really talked about it till recently, and it talks about it in the article, which I won't mention.
Some kind of patent, right?
You want to know?
Was it some kind of patent that they found also that helped them?
Yeah.
It was patented,
Yes.
and that's one of the ways I thought that they learned how to break this thing.
Yeah. There's some secrets of how he found it. He didn't just sit down on a table and start. He did some investigation, due diligence on it before he started. But before he was asked about it, he had no clue. He was asked, "Hey, can you do this?" And he goes, "Well, I like to figure stuff out." And the guy goes, the general, whoever, said, "Well, France and U.S. has given up on it." He goes, "Well," and he had seen some of the papers this kid had written. By like at 23, he was a genius, and he was 27 when he sat in front of this general. But he's pretty modest. He wasn't a big head or nothing. And he said, "Well, if you give me a shot, I think I can do it." And sure enough, they did. Yeah, so.
They steal the actual machine from a sub beforehand.
Do what now?
The actual box.
Yeah.
They had to steal that from a submarine.
Yeah, they had to grab.
So
Yeah,
the
you had.
story
Yeah.
goes even further.
Yeah, exactly. Yeah, they had to have something to start with, right? To be able to for him to look at.
Stealing the Enigma machine.
Exactly, they had to have a real Enigma machine to start with. But what's cool about the video, and I'll stop talking about it, but what's cool about the video report they did was at the end of it, they showed the actual computer that this guy built and his team, and it's actually still functional. It still works in this museum. It's crazy. So in computer cryptography, a key is simply a binary number of varying length, depending on the type of cryptography used. There's two types, symmetric and asymmetric. Symmetric is basically where the cryptography generally relies upon 128-bit or more encryption key. Asymmetric is cryptography requiring keys of 1,024-bit length, or typically today 2,048-bit. Asymmetric going both ways. So you have encryption going both ways, encryption and decryption. A properly generated key can only be cracked by brute force, and only then after thousands of years, even at today's processing speeds. This presentation is about 2 years old. Still, it take hundreds of years to crack encryption key technology today. So here's basically encoding and decoding, and it is very oversimplified example here, but one typical way keys are used to encrypt and decrypt is by using what's called in divisional statement the XOR logic, the leftover divisional statement. And if a bit is to be encrypted is the same as the corresponding key bit, the encryption bit is 0. If it's different, the resulting encryption bit is 1. Without the key, you can't be sure what the original bit was. Simple keys like this are vulnerable to known text attacks. So text 0, key 0, result 0. Text 0, key 1, result 1. Text 1, key 0, result 1. Text 1, key 1, result 0. And all Turing did back then was you had basically letters A through Z and all the numbers and all the, I think that's the only thing they used. I think they might have used punctuation, but not for sure. He just went through a series of logic algorithms and had to create a machine to do it, to go through all of these different brute force attacks basically on every single letter and number that was coming through. Symmetrical cryptography relies on both the sender and recipient having identical copies of the encryption key or access to a third party. And basically what we're talking about here on symmetrical, the one we're going to do Thursday, basically is you will have a public key of mine if I was to set up trust with you, and that public key would match my public key as well. But it would actually be sourced from a private key that I have, that I create. And from a private key, which is only one, you can create thousands of public keys from one private key. So you can use relatively low key lengths, like 128-bit, 56-bit, 128 bits or more is less likely, is less standard. 56 bits has been cracked before. So we go in today's world about 256-bit to 1024-bit keys that are created. The problem here, and we'll mention it Thursday again, is the secure key distribution. The one we use on Thursday, the way it's built in to the PGP is using public domain, usually on educational colleges like this, give certain servers to host these keys, these public keys, and then folks can use that freely at no charge. And it's generally universities, but there's other companies that allow to use server space to do it. So because of that, granted, in order to, if somebody was to grab a public key and not have the original private key that was created, it's pretty useless, but there's still some shot at de-engineering that public key to find out what the private key is. Again, it would take literally hundreds of years at most times, but it's still possible to do. So what happens here in the asymmetrical cryptography public-private key scenario that we're going to do Thursday is the sender will generate a public-private key pair. You guys will do that Thursday. It'll ask you to also save local a key file, and that key file's for the timeline or time for that key to live, so it can be from 10 minutes to infinity, never expire. But you could put on their time frame and say 30 days out, this key is going to expire, and the life cycle of this is going to expire. And so a lot of times in governmental or even during wartime, when emails are sent during encryption, they'll lengthen that time to be shorter and shorter. You can even set it within 24 hours, like I said, 10 minutes, 5 minutes, whatever. It's published on a website, and email signatures as well can have public keys. Some people put them on the back of their business cards. A private key is guarded at all costs because if it's lost, corrupted, or compromised, a new pair must be generated and all that start over again. All of your contacts must be notified and supplied with a new public key. So it's important on those private keys for businesses when they create a private key to have that backed up on a server to where no chance of this is going to happen. If somebody was to delete it, they can just restore it from the backup. Data encryption to the public key can only be decrypted by having that private key. That's the only way. And when we go through and set up the trust Thursday, you will send me your public key. I look at it and see it. I right click on that public key and I say, I can ultimate trust you, or I can give you limited trust or whatever. We'll say ultimate trust on Thursday. And then basically what it's doing is, once I give you trust on my machine that you are who you say you are, it basically, that public key you've given me is tied intrinsically to your private key on your machine. I have no access to your private key whatsoever. And vice versa, when I send you my public key, you can trust it. And then once you trust it and hit apply, it goes back to my machine to see, okay, does this public key match my private key? If it does, then that trust is made. If that private key is deleted on my machine, and you were to trust me, it would say fail, wouldn't work. And so that private key has to exist all the time that public keys are sent out to those folks. Data encrypted to the public key can only be decrypted by the private key and vice versa. PGP is based on public-private key cryptology. Again, oversimplifying a bit again, they're essentially based on mathematical operations involving two really large prime numbers. Prime numbers can be proven to be known to have known predictable pattern, so that's why they make them really large. Remembering factoring from what's called third grade math, you can use it's easy to factor the small numbers into primes, 14, 29, 49, etc. Even, divisible by 2. Digits add up to a number divisible divided by 3. Then 3 can also be a factor. Then digits divided by 5 or 0, divisible by 5. But it's a lot harder as the numbers get bigger and bigger to start doing the prime factoring. And that's where the encryption comes in, or the hard cracking comes in, is because it's a very large prime number to start with. They do this encryption. So here's an example of a prime number. What is this number? So 2 to that number there minus 1. To write it out in the decimal form, it would require that number 7,816,230 digits minus at 1 digit per second. It would take more than 90 days nonstop to get to the bottom. Okay, just for that one example. Currently, the largest known prime number is this one right here. And there is a site he puts on here, primes.utm.edu, largest.html, a really good site for stupid number tricks. It is a pretty cool site too. So PGP pair strength, private key pair strength. When you go through the steps on Thursday, one of the things you have to go through is setting up the strength of the key. You put a password in the key. You put the lifespan of that key. You put a password in that as well. But the public key is mathematically derived from the private key. The private key relies on computational difficulty of deriving large prime numbers used to generate it. It's usually in the 2048 standard today. Keys over 2048 are more secure, but tend to eat up more processing power. Some keys use what's called an RSA standard, but most keys nowadays are generated by the Diffie-Hellman standard. Even at these lengths, known text attacks are a danger and the brute force. So algorithms for this used to induce randomness in encoding messages. Algorithms also help reduce known text vulnerabilities. So encrypting algorithms are designed to do what's called to be reversible. Then they have to be, because some of the well-known ones that we've used so far, we've used Blowfish in here for AES in here for last week's TrueCrypt. These basically are designed to be reversible so they can be unencrypted once they've been encrypted. Hashing algorithms are one way, irreversible. They're used to provide a signature, which you'll create Thursday. They're also used to provide a shared secret verification, which you'll provide Thursday as well, and a certification, which will be created. It's used for password storage on most operating systems, and well-known ones are using what's called MD5, SHA, which PGP uses. So on Thursday, when you guys create the public-private key, you'll actually create a certificate with a password, with a lifespan, with an encryption like AES, RESA, RSA, or the Delphi. And then once that's created on your machine, then you are then able to create a public key from that private key. You'll actually have a visual interface where you'll see your private key. You'll right-click on it and create public key pairs and be able to send those via email, and that's what we'll do on Thursday, or upload it to a server, which we won't do on Thursday because it takes a lot of time. Here's an example of what MD5 would look like if you were to intercept an email. Okay, so intercepting 1, 2, 3, 4, 5, output would be that there. Okay, on an MD5. And so if somebody was to intercept your email that was encrypted, it would look something like that. And on the handout we do Thursday, on the front page is a screenshot of what an encrypted email looks like if it's intercepted. So without that decrypted key, without that public key, it's pretty well useless. PGP encryption algorithm is applied to the data. The appropriate key is applied. The private key, if encrypted your own file data. Recipient's public key if sending email. So what happens is once you guys set up the trust on Thursday, there'll be a little green check mark as you receive and send your emails to each other. And when you send an email to each other, you will sign it and encrypt it, both. The signing is a certificate of signature, and then the encryption key is sent across the email. On the other side, you open it up with your PGP email client. It notices you, sees that encrypted key in the email, and if you are set up as a trust user, it puts a little green check mark and you can see the email. It says it's been decrypted and you've been unlocked to see. If you get an email that's you've not set up a trust for, like if I send you one and we've not set a trust up, you would just see gobbledygook on the screen. That's all you would see. You'd still see my key attached to the email, but if I haven't set up trust with you, it's not going to be able to do anything with it. Does that make sense? So really, there's no danger to include public keys within an email if somebody does intercept that, because if there's not been that public-private key trust set up, it's not really going to matter anyway. They're not going to be able to do anything. The second bullet here where it talks about they are not secret, talking about, in fact, they are made public, the public keys, and they're subject to rigorous testing by mathematical peers. The algorithms that are used in PGP are constantly updated. The encrypted algorithms are reversible. They have to be able to decrypt them. Applying the key before the algorithm is pointless because the algorithm can be reversed, leaving the key exposed to known text and brute force attacks. So where is the security? In the public-private key cryptography environment, the strength lies in the length and protection of the private key, not the algorithm. Okay, so the length of that protection key and not the algorithm and the private key. And so basically it's your time frame, and that dates back all the way to the Enigma machine. The time frame was 24 hours. It changed every 24 hours. So that's where it lies in the security of. And you would change technically if you were setting up this type of thing for communication, you would change it every 30 days. You would change it at least every 30 days, at least, if not more. Depending on the security of what you're doing, you might even change it sooner than that. It might be every 24 hours you change the encryption. It might be every time you change the encryption, public-private key. Again, it depends upon the sensitivity of the data, because it is hackable if you have the right software. It can take tons of time, but if you kill the date in 24 hours, it's pretty much impossible. And that was amazing about the 1944 thing with the Enigma machine. You didn't have computers back then. This guy had to create something from scratch. There was nothing back then to do this. And so, I mean, we have all the technology today. In fact, I was reading some article after I watched the CBS news piece, and it was saying they're interviewing some guys from like MIT and computer science, and they were saying that all of our modern day cryptography and even computer science field can date back to what this gentleman did in 1944. Yeah, just blows your mind. So digital signatures. Basically on this one, it's usually applied to the email messages, and it just verifies that the sender is who they say they are, their identity. And you will sign your email Thursday before you send it, and your digital signature signs a message with your private key. The hash algorithm's applied, and you send the email. Anyone who has a sender's public key can apply it to and verify that you are who you say you are. So that's another thing about digital encryption on email is if somebody says they didn't send an email, if they sent it via this encryption process, they did send it because it's on their machine, number one. Number two, they have to sign it and encrypt it before they can send it. And so it'd be near impossible for them to say they didn't do it. Now, granted, somebody might have came and logged onto their machine and sent it. Maybe they didn't send it, but it was sent. And so you can verify that that email was sent with encryption because it has a timestamp, verify signature. So anyone who has a public key can decrypt it if they have the corresponding private key. Here's an example here of what a message would look like in a key block using the PGP privacy. If somebody was to intercept it, man in the middle, right? This is what it would look like on the key block. And what's happening here is the encryption here in this case, it's the same every time. It shows the beginning of the key block here, the public key block, and then at the bottom here, it also shows the ending of that public key block. Now that's just for the public key. That's for the public key only. It has nothing to do with the message. So what you're seeing here is not even the message, it's just the public key in all text. That's really meaningless without the private key. So public keys can be, because of that, published on a website, carried around on floppy disk, which nobody uses anymore, CD-ROM, USB, jump drive. I haven't heard jump drive in a long time. To people to copy it. You can send it as email attachment like we'll do on Thursday. Thunderbird actually has built into the PGP screen a right-click option where you can send public key to anybody via email and then upload it, or you could upload to a key server. Print it out on a sheet of paper. I believe the modern day Microsoft, I believe you did it here, one of the options you mentioned last week. It does allow you to print out your public key in Microsoft's latest version of encryption. You could do it the same here. And you could rent a billboard. Well, you get the idea. So how do you know it's really your public key? So generate public private key does not require any authentication. You can associate any name, email, or address with a key pair you choose. Now on Thursday, we do use your email. It does also use your signature. And it also uses the current computer timestamp, I believe, something like that, to make that algorithm work. So to be completely certain that a given public key actually belongs to the person it claims, you need to physically verify the person's identity and key in person. So this guy recommends asking for a photo ID if necessary, ask the person to read the fingerprint and verify against a printed copy. Verify printed copy, fingerprint against the electronic copy, and what he's talking about fingerprint is that public key fingerprint copy to make sure it's the same. Is it signed? PGP public keys can be signed by other third parties, verifications. If the signer's public key is one that you already have, you can use it to verify the signature. If you can trust your signature key, you can trust the signed key. And I think in the PGP we use Thursday, it gives us everything from limited trust to ultimate trust. And ultimate trust means anything they send you attachment-wise, whatever, is going to be trusted in that exchange. So PGP is built on a web of trust, built on a network of transitive trust relationship. If Tom trusts Dick and Dick trusts Harry, then Tom can trust Harry, basically. And so it's basically that circle of trust, web of trust within that domain of private key. Only in the context of identification and authentication, it doesn't necessarily mean Tom is assured Harry is a trustworthy person, only that he really is Harry. And that's important when you're dealing with sending and receiving data. Functions as sort of an ad hoc certificate authority. The more links in a chain, the more likely there's a weak link somewhere along the way. Key signing parties, opportunity for several people to get together and exchange public keys, held regularly by ISC information security folks, where they print out, they put on a card, put on a thumb drive, website, whatever, email key at the bottom. Security will verify all identities and distribute them to all attendees of some of these events. So here's an example of what, actually, you'll see this kind of screen on Thursday. When you get, somebody will send you a public key, it'll have their user ID, which is going to be their name and their email. And then the way we use on Thunderbird, instead of the slider here, you just right click and it has a whole bunch of radio buttons that you choose from minimal trust to ultimate trust. So all the way to right here would be ultimate trust. And then notice here, some of these have creation date, all these have creation date, but some of them have expiration dates. So this one started at 6/18/03 and it ends on 6/17/04, and then that trust is over. That public key is dead. Can't use it anymore. And then this one here is about a year. This one here is about a year. So all of them looks like it's about a year. This one's 3 years here. And you'll also notice it has in here the different types of encryption that was used, from Healthy Newman, DH to RSA. So that's kind of what it's going to look like on Thursday. And some of these you'll notice here on trust, like this one, they give an example, abuse at 3com.com, it gives no trust and no validity to it. This here is an example of the PGP encryption screen when you trust. And we'll do the implicit trust on Thursday. And basically in the fingerprint encryption, it basically, you can it puts in there multiple keys to make that encrypted fingerprint. And then it tells you what type of encryption it is, a healthy on this one, the size of the key. And you'll also have a password that you'll put in on that key as well before you create the expiration or no expiration date. So this one here is never expires, and its size is 2048 encryption key. And here's an email. And you'll notice here in the email, the signature over to the right, it looks a little different on the one we're using Thursday. On the one we use Thursday on Thunderbird, you just have one button that you just click on that says sign and encrypt, and then you send it. You sign and encrypt, and you can actually set it up as default to send that way. And so say this person has a trust set up with John, he writes him a message, and signs and encrypts it and sends it. And the other person is going to receive that message as decrypted on the actual email. This one here, on this system they're using, they have to enter in a passphrase every time they send the message. The one on Thursday, we have it embedded in the email, but you can set it up to where the user has to enter a passphrase every time, which will add a little bit more security to the process. So, PGP encryption, Thunderbird. On Thursday, we'll be using the open source Thunderbird. You can download it if you want to between now and then. If you want to bring it on a USB drive, you're more than welcome to do that. Otherwise, we'll be using the desktops to do the lab on Thursday, and then if you wanted to move it to a USB afterwards, you may do that. I do recommend creating a Gmail account, and maybe just to help you if you want. Some of you already created one, but pct130, f14, and then maybe if you want to put in the year you were born or something at the end of it. More than likely, that is going to be available in Google Gmail. More than likely. I'll say, well, that's a good shot there anyway. If you use that logic, more than likely that'll be ready. And then if you wanted to kill it after the lab, that's fine. But I always do just create a free Gmail every time we do this. When I first started creating this lab, I think I had a pct130 generic email I used, and I just created like, I don't know, 20 of them or something. But over time, like say after the 10th year of teaching it, that's your 20 courses, the Gmail's got quite full. And so, you know, because one of the things it does, if you don't check it real quick when you set up Thunderbird, is it says, do you want to download all your mail in your inbox? And if you forget to uncheck that before you set it up, it downloads all your email.
And deletes it from up top.
Yeah, and if you're on, you know, if you're like me,